Let's review our implementation. We'll zoom in to focus on the data flow from browser to web to logic tiers. The web browser communicates with the machine at the presentation tier over HTTP, while the servers in both presentation and logic tiers communicate over WebSocket. We will set up a WebSocket server in the machine at the presentation tier, and a WebSocket client in the machine at the logic tier. We want to configure both HTTP and WebSocket servers as separate ports. This is even though WebSocket normally shares the same port as the HTTP server. And we will need to be mindful of properly serving requests from multiple web browser clients, all channeled through the same single WebSocket connection. I will be using Node.js with third-party libraries, but the concept can be realized using just about any programming language and framework. To interact with web users, the HTTP messaging will be handled by the popular Express Web framework. Next, while there are many WebSocket libraries available, I have chosen to use Socket.io because it's mature and feature-rich. This means configuring the machine at the presentation tier to double up as a WebSocket server, while the machine at the logic tier will run as a WebSocket client. For development, I will use a self-signed certificate to secure the WebSocket connection. An OpenSSL command like this will suffice to generate a pair of SSL certificate and private key files. Note the localhost IP address specified. You'll need to move the cert and key files to your Node.js project folder for use. The machine at the presentation tier hosts a couple of important files, a indexserver.js file for the main server program, and a index.html file to be served to a user's browser. While in the machine at the logic tier, a indexclient.js file runs as a WebSocket client. Let's look at the main indexserver.js server file. At the top are references to modules we need, including the Socket.io and Express modules. In this two lines, we bring in any port values that we might define during runtime for the HTTP and WebSocket services. This flexibility allows us to fit any desired deployment scenario. Here we declare EJS as our view engine, although we won't be using any EJS templates. Next, we declare references to both the certificate and key files. You may recall we created them earlier. Next, we declare a location path that can be used for serving static files to the user, and to send index.html in response as the site's landing page. Let's move on. We configure SSL for the HTTP service by pointing to the certificate and key files. Then start up the HTTP service at the designated port. Next, we create another HTTP service, but this time set to the designated WebSocket port. Let's keep going. We declare a Socket.io instance writing on the last HTTP service, and make sure to specify only to use WebSocket transport. And for added security, we can check and only allow connection from a Socket.io client of known IP address. In this case, we just set to localhost, since everything is running from my development machine. Let's keep going. In the remaining code here, we pay attention to the WebSocket connection events. Note the security check for a valid handshake token. This token is optional, but can be used to further ensure a trusted connection. Here we check for a static string from the Socket.io client, but it could instead be an environment value set during deployment or runtime. The next few lines are boilerplate Socket.io events we can tap, but we don't actually do anything with it. The same goes for displaying details about any connection error event to guide development. Now, let's add the code that will facilitate data transfer between browser and Socket I/O client. I'm creating a single HTTP post endpoint, which will be called from the browser. I make a reference to the request body because the payload contains an item ID to be passed over to the next tier. We can pass the request body into a new function which will take care of the transfer and await for the result. With the result, we will pack it into a JSON object and send it back to the browser as the response. And alternatively respond with an error message if the result is empty. I now create the internal async function that will perform the actual data transfer over WebSocket. I need a reference to the existing Socket I/O client that we are connected to. We can get all connected clients with the fetch sockets method into an array. Of course, we only operate on a non-empty array. While we expect only one Socket I/O client, here, my code will randomly select one client out of the array. This is in case we ever decide to scale using multiple clients in future. If a client exists, we then proceed to use the emit_with_act Socket I/O function to send the user's request to the Socket I/O instance at the logic tier. You can chain a timeout and wrap a try-catch block around it to ensure the user will at least receive a response without waiting indefinitely. Next, let's look at the code for index_client.js, which appears in the machine at the logic tier. We begin by making a reference to the Socket I/O client module. Next, I specify some configuration parameters for our Socket I/O instance, including defaulting to WebSocket transport, enabling secure connection, auto reconnect after 1 second failure, allow unauthorized self-signed certificate, and applying an auth token. We again declare use of dynamic values for the WebSocket port and server name. And with that, proceed to make a connection to the Socket I/O server at the presentation tier. Moving along. The rest of the code here is with respect to Socket I/O connection events, which you can paste from their online documentation. You can pause the video as I scroll to inspect the syntax. It's good to cover all the key events, including connect, disconnect, and reconnect. Now let's add code to handle the incoming message from the Socket I/O server. We act on the message key. In this case, it's called fetch this. I will only echo the received data using a callback, but in reality, this would instead be a database query result that goes into the callback. That's all for this file. Let's next go back to the presentation tier to look at the index.html file. It's a simple HTML form with a drop list of items that the user will pick from. You can pause the video to inspect the code as I scroll. Once an item is selected, we extract its value to be posted to the web server. Here we can see the call to the web server endpoint that was defined previously in indexserver.js. The results from hitting that endpoint will be formatted and displayed on the browser screen. Let's run the app next. As we are using a self-signed certificate to enable TLS, we will need to force the Chrome browser to accept it as well. On Windows, you can do this by creating a PowerShell file with the sh extension. This screenshot shows the commands that work for me. Here, it's launching my local copy of Chrome with a switch to ignore any errors due to the self-signed certificate. It also tells Chrome to load the homepage URL of the application. Finally, we can launch our app. I'm using terminal panels within Visual Studio Code, but you can do it with multiple command prompts as well. We want to use Node.js to launch both the server and client index.js files. The order doesn't matter because the client will keep trying until it connects to the server. Next, we will run the PowerShell file to launch Chrome straight to our home page. Chrome allows the SSL connection. We can ignore the security warning message at the top. The test is simply to click the drop list items and observe the responses, each signifying a round trip into the logic tier, as we expect. There is also no significant delay, thanks to the efficiency of WebSocket messaging. In our next video, we will perform some validation of our implementation.